Okay, so with that out of the way, without further ado, let's jump into what we're going to be talking about. So we're going to recap deep learning for those of you who don't have that much of a background. We'll be talking a little bit about convnets and stochastic gradient descent. We'll talk about the differences between the supervised and unsupervised learning. I don't know if you went to the previous talk, but obviously, something like time series would live in the supervised world, so we'll talk about the exciting unsupervised world. We're going to talk about a little bit about where GANs kind of came from, and then what was their sort of origin story. And then we're going to walk through two architectures if we have time, and possibly through a slightly adjacent field, but a field that I think is sort of underappreciated amongst sort of deep learning professionals. So, deep learning review. We're gonna do the first thing, which is convolutions, right? In a typical deep learning setup, you have this fundamental concept of a convolution, which is a way of transforming your raw pixels into some higher order feature maps. This is going to be important because we're going to be using this operation and the opposites of the operation, where you basically go from sort of wider and from more height and more width into sort of more representations of the same picture, like so. So what's happening here is that we're starting from the standard image, in this case 227 dimensions by 222 2 pixels in 3-dimensional color space, right? So we have 3 matrices, 227 by times 227 times 3, right? So 3 color channels. And as we go through the network, we sort of create higher level representations of this wolf, right? So, and we start to pick out some basic features. So in the first layer, we're starting to look at like the edges of this picture. And then as we go onward, we have more sophisticated feature detectors of bigger concepts because the receptive field grows. Hopefully they'll clear out basically on some level it's possible to come up with better representations of the same picture that will be more understandable to the computer, if that makes sense. So if the mathematics is too convoluted, don't worry about it. But basically the core idea is there's a mathematical operation which allows us to go from basically just a color channel matrix into representations that start to be meaningful, that we can say this is the edge of this facial feature, or this is, the whiskers or whatever. Like we're starting to create these representations automatically as we go higher up. There's also the opposite of this operation where you go from sort of features into basically the full image. You say, here's like a whisker detector, and you sort of go up and up and up, and you expand that dimension into a whole picture, which is called transpose convolution or deconvolution. We're not going to go into it, but just so you know that it exists. So that's the process of, here's some pixels, they're just numbers, how do we get to something that's meaningful, right? I'm brushing over some stuff, so if you actually know deep learning, don't kill me, because there's some detail that I'm rushing over. So, okay, that's all well and fine. How do we then use that? Well, ideally we get a lot of grad students and we point them at that problem and they'll figure out how to solve this problem. But in actual fact, we use something called stochastic gradient descent to update how the operations should transform those raw pixels into an actual feature. So does that kind of make sense? We're basically backpropagating, we're measuring the error at every step, and then that gives us a loss, and then we use the derivatives to basically move down the loss space. People with me? Sort of? Some hesitant nods. Basically, there's a training process, right? So we're trying to come up with a mathematically rigorous way of updating how those operations should be stacked one another in order to move down this loss space, right? So we have some like some 3D representation of this loss space, and we're trying to go to the minimum, like standard optimization problem type thing. Reasonably clear? Okay. So this is kind of what I define, like this is the most simplified view of deep learning you'll ever find out. We have some features X, basically some bunch of images. We run that through some function, which is our deep learning, which is our neural network, and we get out some prediction y hat. And we measure the loss, which is the difference between the true value of that label. Maybe that's a label of a cat or label of a dog or whatever, and our predicted label. Right? If we make a mistake, we get a bigger loss, and then we're basically trying to optimize this feature, this function, so that over the possible parameters theta, so that we minimize this loss. And then the last step is just updating those parameters theta at every step with the derivative of the loss function with respect to the parameters. If you know mathematics, hopefully this helps. If not, we're gonna sort of move on and then sort of deal on a higher level of abstraction. So hopefully, if this will sort of, you'll still get to understand the rest of the deep learning magic. Okay, so learning without adult supervision. So as we kind of saw in the last case, here we have some sort of in a supervised world, we have something like a time series. We extract possibly some feature vectors, right? And then we have this machine learning algorithm that gives us the labels. So in the time series case, for example, that would be just the next step, right? The value of that time series at the next point. So that would be our label. And then at inference time, i.e. when we actually want to run some predictions, we'll get this new time series. We extract the same feature vector, and then we run it through the predictive model, and we get the forecast out, if that makes sense. So obviously, in deep learning case and in case of imagery, we get the feature vectors that are extracted for us. That's the process that we talked about in the convolutions. And then we get the labels could be still like something semantically meaningful, like a cat or a dog. And we basically kind of use that at training time, and at inference time, we get a new picture of a new cat, and we say that's a cat because our model is already trained. Everyone good? Yeah, okay. Cool, so generative modeling. So generative modeling lives in this sort of unsupervised machine learning world, right? And obviously, like, you know, we've been fascinated with creation, well before Richard Feynman, but obviously he was one of the ones to make the code I cannot create, I do not understand. I think there's something really profoundly meaningful, especially when you think about even, this is the data set, the MNIST data set, it's like the hello world of computer vision, and it's really the sort of basis for all the machine learning models that kind of came afterwards. So it was really the proving ground of can we actually make any reasonable computer vision algorithm. And even in such a simple case, so MNIST is 28 by 28 grayscale images, so that gives you about 784 dimensions. That's not very much, but at the same time, the mathematical functions that define a digit in this space can be very complicated, because obviously when you flatten it into a vector, you would have very, very weird probability density function. For those of you who are not mathematicians, just remember that this is like basically an interesting mathematical problem, probably not much more than that, but it's actually pretty hard to even come up with a good way of mathematically generating these very, very simple images. So unsupervised machine learning, and especially generative modeling, has been generally underappreciated because we struggle to make even supervised machine learning work. And obviously, the point of this whole entire task is to come up with examples that look like they came from the same data distribution as our initial training set. And to this end, we're using some learnable function generate that hopefully is parameterized in such a way that we can use stochastic gradient descent to backpropagate through both networks. So this is another look at MNIST. Here, basically, you take MNIST, flatten the vector, use PCA to reduce the dimensions down to 3. Principal component analysis, if you know, if not, doesn't matter. It's basically just a dimensionality reduction technique. And now think about that already. This is already kind of hard to reason about this. And obviously, there's the colors mean different digits. How would you even start reasoning about how would I create a new digit if I wanted to, mathematically, right? Like as humans, we just write it down. But as mathematically, the density function that actually defines a digit is very complicated. There are actually approaches trying to do this, like pixel RNN, but we're not going to talk about that. Know that it's very, very complicated and does not scale terribly well. So how would we even generate it using machine learning? For now, let's just assume we have a trained model. We're going to change that assumption in a little bit. So in this case, we're going to start with something like an autoencoder, which is much easier to sort of reason about. We basically sample from a random seed. We want to basically come up with some inspiration so that we don't generate the same example every time, right? So we need to have some sort of random seed to say, you know, this time the digit should be 4, this time the digit should be 1, or something, or a slightly different one, right? Or slightly different 2. We need to have like many representations that could come up with like differently looking digits 2, differently looking digits 3, and so on. So we sample from this random seed, we run it through this function using the deconvolutions we talked about, and then basically get the output, right? So that's like the sort of 3 steps, right? We have this latent vector, which is the sort of inspiration. We run it through the decoder, outcomes and output. Okay, so that's all well and fine. So far we haven't got to GANs, which we're doing right now. So obviously the key assumptions we made in the previous slide is that we actually have a trained model. So what if we do not have a trained model? Well, there's no reason for that yet, right? Like we're just sort of, this is just the proving ground. We'll get to why that might be interesting in a bit. So what are generative adversarial networks? So let's work backwards. Networks, there's 2 of them, adversarial, they're competing with each other, they're generative, right? So we have generative learning. And what's happening here is that basically we sample from the latent seed at generation time. We run it through the generator the same we did in the previous slide, and then we get some notion of an MNIST digit. On the other hand, we sample from the random data, from the real data randomly, and then we sort of compare the generated digit that our generator produced and the real digit that we have from our training data, which is the discriminator's job to tell which is which, right? To start to understand this is how real data looks like, and this is how fake data looks like. And then out comes a classification. So from discriminator's point of view, this is just a binary classification problem, nothing new. Generator is a little bit new because now we have these series of deconvolutions that lead from random seed all the way out to a digit. So in other words, generator inputs is inputted with a vector of random numbers, out comes a digit, and obviously we're trying to generate data that looks like it's indistinguishable from the real training set. And then the discriminator basically is trying to discriminate or tell which digit came from the real distribution and which digit came from the sort of fake generated distribution. And then the output is the likelihood that this digit is real or fake according to the current parameters of the discriminator, what the current discriminator thinks, right? And then obviously we're trying to distinguish between the samples coming from the generator and the samples and the real examples from the training data set. So an analogy that people use, if that, you know, to start to reason, and I appreciate this is an intuitive concept. It's like, imagine you're sort of some owner of an art gallery, and you're trying to hire a detective to tell which of the images, or which of the pictures and paintings that people send in for them to be exhibited are real, and which are just forgers of some Da Vinci painting or whatever. So obviously, some people go out and forge this. The generator, the forger, sort of comes up with some notion of a lost Da Vinci painting. They send it in. The detective tells this is not real. Therefore, the generator gets an increase in their loss function, right? So they have this loss because now they have sort of lost the battle against the detective, and they get better, right? So they backpropagate the error through gradient descent, and then send another picture in. And this time, maybe the detective gets fooled. And so then the detective backpropagates the error, and sort of both improve through this sort of competitive dynamic. So this is really what I was trying to describe here. Basically, we sort of iteratively train both the discriminator and the generator so that they get better over time. So for those of you who are familiar, this is kind of similar to like sort of mathematical from mathematical game theory. So it's basically a min-max prisoner's dilemma, if you're familiar. Basically, the two loss functions, in one case, it's just a binary classification loss. So for the discriminator, the loss function is literally something similar to what we would use in a classification problem. And then for the generator, the loss function is just the negative, the inverse of the discriminator. So they compete against each other, and one of them sort of has to lose in order for the other one to get better, which is the original formulation, the min-max game, which doesn't actually work terribly well, but it sort of describes this dynamic where you have this sort of landscape of the loss like we had from a couple of slides ago, and basically you can imagine as if one player is trying to go up the hill and the other player is trying to go down the hill, right? So you basically get this like competition. This is a picture from a Uber research paper that tried to connect like Metropolis, Hastings, Monte Carlo simulations to GANs, which is actually a cool paper, but we're not going to go into that. Then the same original 2014 paper actually proposed this non-saturating loss, with the only difference that now we have sort of decoupled the two loss functions from each other, and basically now the generator has something that's directionally still against the discriminator, but no longer are they sort of they can sort of allow for better learning mechanics because they can sort of start to understand in the early parts of the gradient. Basically, it gets around this sort of vanishing gradient problem, which is a theoretical problem in deep learning, not just in GANs. So why is this an interesting problem? So following that question earlier, right? So generative modeling has been largely unsolved, and we're now moving closer to unsupervised learning as a workable paradigm. So Jan LeCun, who is the director of research at Facebook AI, has sort of called GANs the most interesting idea in machine learning in the last 10 years. Also, there's a number of people who, kind of say like the revolution will be unsupervised. Why? Because labels are really expensive or really time-consuming to get. And you think about even the previous talk in time series, the problem is actually of low sampling, right? We can't sample faster than the real time. Whereas what we would actually want is something that just goes out and irrespective of any human guidance, just figures out what it needs to learn, right? And this is kind of how we move closer to that paradigm, from something that's really handheld, where people have to explain with every single example, or through some generating process, what each example means, to a world where sort of the machine learning algorithm can figure some of these things out on its own. There's lots of applications in semi-supervised learning, representation learning, data augmentation, image in-painting, and in general, there's a Cambrian explosion of downstream applications. So in even academic papers kind of start to look at, okay, we made GANs work, now what's the next step? So how do we progress from something that's a relatively uninteresting MNIST example? Well, the first, I can't really see that. Okay, so actually one of the things that I was going to say, so all these image transition slides, none of these images are real. They're actually all generated by BigGAN, which is work from DeepMind, where they manage to generate 512 by 512 fully like realistic images for all 1,000 classes of the ImageNet data set, which is actually kind of incredible, given that they have to come up with realistic sort of impressions for every single breed of cat that's in ImageNet, every single truck. It needs to learn so much about the world, including geometry, and sort of, different, like the fact that cats have particular structure of the body and so on. So it's actually an incredible achievement. So one of the first GANs to get there was called the progressive GAN, which is the state of the art in about early 2018. And basically, it kind of came up with this idea of progressively increasing the complexity as we learn. So basically, it's been only beaten by very few GANs since then, and sort of has managed to get from something simple as MNIST all the way to pretty complex images. So in this case, all of these are full HD images generated by the GAN, completely synthetic. There's not a single person that's real in those images. And we can get to that level of actual realistic looking full HD images in about a couple of days training on a GPU these days. So it really went from, in early 2014, from like really uninteresting sort of MNIST data set all the way up to like 1024 by 1024 images that number of different GAN architectures actually support. So again, why have we done all this hard work? Obviously, GANs are hard to train. There's a lot of complexity, but ultimately, this is really worth it because it's a real step change, right? There's no way you generate an image with a linear regression, right? We're now in this part of the game where we basically can come up with things that traditional statistical techniques just would not have any way of reasoning. This is actually called SPADE or GAN, which is also from another lab at NVIDIA. And you can see that as you draw and provide a semantic label for the image, it can synthesize, based on your prescription, a full HD photo in different styles and sort of make adjustments logically, right? So you can see as they scribble a little bit of the land here, right? The GAN is like, well, but that doesn't make sense, right? Like, why would there be like a tiny slither of land in the middle of a sea? So it suppresses that as far as it can. And then when you color that in with a sort of bucket style MS Paint tool, it figures out, oh, okay, that's a beach, and then it fills it the rest of the picture accordingly with that understanding, right? So it really learns something fundamental about this world and how we basically need to stack this on top of each other. So this is just one example. I think there are now open source models that sort of replicate the same functionality. And sort of allow you to run. Also, if you want to try this, there's a startup called Runway ML that allows you to like train these things like for artists. So you can sort of have a play around. I don't know if that's implemented, but I think they talked about it. So another example of how we use semantic labels, right? We just say, I want a person here, I want a car here, I want a road here, and then it generates a fully synthetic image. This is done on the Cityscapes data set. So you can sort of see that it kind of gives you these Germanesque looking cities because all of the data set was that gathered in Germany. So CycleGAN, I think I'm going to just go through that very quickly. Basically, CycleGAN is a new approach to domain transfer. So I'm sure you guys have seen style transfer, where you take like a Monet, like a Van Gogh painting or Monet painting, or like a Star Unite, and then make all of your holiday pictures look like they came from this famous artist, right? So CycleGAN generalizes that across many, many domains. So obviously, you can go from Monet to photos, or the other way around for the first time. You can go from horse to zebra, from zebra to horse, or from summer to winter, or from winter to summer. And even sort of, it works pretty well, but it's not perfect. You can even go from day to night, or night to day. So it figures out how to fill in the details that it might not even have, just based on what it's learned about the structure of the world, which is a fascinating application. I'm not going to go through the architecture because we don't have time. Adversarial attacks, don't really have time for that. So I'll just probably contextualize that a little bit. What have GAN achieved? So remember, unlike most of deep learning, which the basic building blocks for deep learning have existed since like 1998, And we're only getting to that now. GANs have really only made work around December 2014, or well, that was when the paper was presented at NIPS. And since that time, the original GAN paper has gotten more than 2.5 times the amount of citations that the original TensorFlow paper has, right? Like, which is kind of incredible, given that TensorFlow is like the fundamental tool of machine learning these days. We have lots of fascinating applications like spectrum normalization, big GAN, which is the images that were, I think, hard to see. But we're also moving ahead in terms of software engineering. So TensorFlow Hub now has basically is like the GitHub of machine learning. So we're trying to basically move closer and closer towards productionization. I think last time I checked, TensorFlow Hub had about 20, 30 different GAN models on it. They're pre-trained and ready to go. So if you want to just use some different types of generation, you can just download this pre-trained model for free off of TensorFlow Hub. PyTorch Hub exists as of about a week ago. So PyTorch, the second most popular deep learning framework, now also has the equivalent with actually many more models and lots of cool integrations for people to contribute. So it's really grown from one paper in 2014 to several thousand now. I think this paper's this slide is a bit outdated, but the academic interest has launched incredibly quickly, and we're now starting to see the first wave of GAN companies. So there's references and links if you want to take a picture of that. People generally seem to want to follow up, but if not, then I'll just do a little plug. So here's the book that I co-authored. We wrote it almost at a level of, if you read something like Deep Learning with Python from Francois Chollet, you should be able to, with a little bit of Googling or maybe a bit more Googling, figure out what we're trying to say here. If you're interested in GANs, come talk to me or message me on Twitter. And then I think I'll take the questions either afterwards in person or on Twitter. So thank you very much.